This video is designed to move you through Module 3 of Miss King's AP Environmental Science class. Module 3 includes information about generalist and specialist species, reproductive practices, species interactions, survivorship, population growth, the demographic transition model, and impacts of population growth. When we talk about species, one of the first things we talk about is whether they are generalist or specialist species. This designation gives us lots of information about the kinds of environmental factors those species will be subjected to and the ways in which they may change their reproductive practices to ensure that their population remains stable. These are species that are on two ends of a spectrum. Some species may fall slightly more in the middle. However, the majority of them are going to fall into the clear category of a specialist or a generalist. Let's look at specialists first. Specialists tend to be those species that have a narrow niche, meaning they have a very limited amount of resources and specific locations in which they can thrive. This is called the zone of tolerance. Specialist species tend to be less adaptable because of those specialized needs and are therefore more likely to become extinct. Because they use a specific set of resources, they are easily affected by changing conditions and what are called density-dependent factors. However, when the ecosystems remain constant over a long period of time, specialists have the reproductive and evolutionary advantage when conditions are more constant. Examples of specialist species include most of our mammals, especially the larger mammals, such as pandas, koalas, elephants, and in some cases, humans. It's important to note that neither pandas nor koalas are bears. On the other end of the spectrum are generalist species. These species have a broad niche, meaning that they have a wider zone of tolerance and more conditions under which they can live. They are highly adaptable, meaning that they are less likely to become extinct. They use a variety of resources and have an advantage when conditions are consistently changing. Generalists can be mammals as well, but they tend to be the smaller groups, such as possums, rodents, and raccoons. It's important to also note that specialists and generalists tend to have very distinct reproductive strategies, which we will look at next. When we refer to reproductive strategies, we are typically talking about the rate at which a population grows through natural increase, or RNI. In this case, we are talking about reproductive strategies that can be designated R, standing for rate, or K, which is the graphical representation of carrying capacity. First, let's look at R-selected species. If you look at your screen, this is the graph that is indicated on the left. As you notice, R-selected species have an exponential growth pattern. This means that there is typically no leveling limit on their population growth. R-selected species tend to have a very small body size, smaller brain size, be more generalists, have larger numbers of offspring per reproductive cycle, and have more reproductive cycles in a year. However, R-selected species do have what is called a boom-bust cycle. This exponential growth cannot continue indefinitely. It will reach a point where it has exhausted the resources of its environment, and the population will quickly crash. If you look to the right of your screen, you will see the graph for K-selected organisms. K-selected organisms show early exponential growth, which will eventually slow and level off when it reaches its carrying capacity, or the maximum limit of organisms that a particular ecosystem can sustain. It's important to notice that even though this says that the growth eventually falls to zero, this is not necessarily the case. The population will continue to go above and fall below the carrying capacity, but for the most part, it will remain very close to that point. K-selected organisms tend to be larger and have larger brains. They have fewer offspring per reproductive cycle and have fewer reproductive cycles per year. they also have a larger parental involvement. This is because there are fewer organisms, and it is important for each individual offspring to live to adulthood. Our selected species, on the other hand, typically have little or no parental involvement in the growth of the offspring. Here you see what is called population overshoot. This is something that I mentioned with case-selected species in the previous section. As you notice, this is a population that shows case selection. There is a clear carrying capacity indicated. The population grows to the point of its carrying capacity, and in this case, actually overshoots it. That overshoot leads to depletion of ecosystem resources, which causes the population to drop. The population drops below the carrying capacity, at which point it can recover. As you notice, over time, the trend becomes that overshoot and die-off becomes more tightly associated with the carrying capacity. So there are not many dramatic population booms or drops in this organism. It's important to note that reproductive strategies and being a generalist and a specialist aren't necessarily the only things that impact the rate at which a population grows. One of the other things that impacts the rate of population growth is a species interaction. These are existences where two or more species interact with one another to either mutual benefit, mutual detriment, or a combination of the two. These are all considered symbiotic relationships in which two organisms coexist with each other. Please do not get symbiosis and mutualism confused, as they are often used interchangeably and unfortunately incorrectly. Mutualism is an example of two organisms living together where both benefit. The best example of this is the bacterium E. coli and the human being. E. coli lives in our gut and is one of the things that we use to break down our food, particularly those that are more plant-based. The E. coli has a habitat and it also receives nutrients, but we as humans also get the added benefit of extra nutrition when the E. coli breaks down those food products. Predation and parasitism are both examples that we would call a positive negative. This means that one organism is helped while the other is harmed. In predation, the predator species is helped while the prey species is harmed. Examples of this include foxes eating rabbits. In a parasite relationship, there are two pieces, the parasite and the host. The parasite receives a positive piece of this relationship because it has shelter and it's also gaining nutrients. The host has a negative piece of this relationship, often because the existence of a parasite makes the host sick. It's important to note that the parasite does not kill the host, as this would be a negative benefit for the parasite. When we look at interactions that are negative-negative, the biggest one that shows up is competition. This is where two or more organisms or groups of organisms fight for a specific resource. There are two specific types of competition: intraspecific, between two members of the same species, and interspecific, between two members of different species. Intraspecific competition can be like two lions or two lion prides fighting for the same food source. Interspecific would be a lion and a hyena fighting for that resource. There are examples where one member of the group is helped and the other member of the partnership is not affected at all. This is called commensalism. An example of this is rayfish and sharks. The rayfish swim along with the sharks and will sometimes eat the debris that comes off of the shark's food. The shark itself is neither benefited nor harmed by this. There's also a reaction where one species is harmed while the other is not affected. This is called amensalism. An example of this would be a cow walking through a cornfield and stepping on bugs as it goes. The cow is not affected by the presence or absence of the bugs, but unfortunately the bugs are affected by a giant cow hoof squishing them into the dirt. There's more to understanding the rate at which a population grows than its identification as a generalist or specialist species its reproductive practice, or its interactions with other species. And these are what we call density-dependent and density-independent factors. These factors occur in the population or in the ecosystem around it and can severely limit or help the rate at which a population grows. Let's look at density-dependent factors first. It's important to note that these are more closely associated with K-selected species, as there were fewer individuals and larger populations are going to be more susceptible to these factors. Space, water, nutrients, and food and shelter are the major density-dependent factors. But we can also look at competition for any of those, as well as competition between members of the same species for mates. If you don't have a mate, it's going to be really hard to get your genes into the next generation. We can also look at predation, disease, and parasitism. Disease and parasitism are really important for us to think about now as we are looking at the spread of COVID-19 and other diseases around the world. Now let's look at density-independent factors. These are those factors that don't really care how many of an organism there are in a particular place. These include natural disasters such as tornadoes, floods, wildfires, temperature, sunlight, the activity of humans, specifically the use of pesticides. You would think that we would only use pesticides when a pest population gets troublesome. Unfortunately, that's not the case. Humans use pesticides indiscriminately, making it a density-independent factor. There are also physical characteristics and behaviors of the organism that they cannot control that have nothing to do with the number of organisms in that particular place. There's one more thing to think about when you're trying to decide the rate at which a population might grow, and this is survivorship. Survivorship is the probability that an organism will live to the entirety of its natural lifespan. The graph you see here shows the three main types of survivorship: type 1, type 2, and type 3. They are also known by different terms, which we will talk about as we go through each of the different curves. Let's start at the top with type 1. The type 1 curve is also known as the late loss curve. This is because organisms tend to survive to the end of their natural lifespan. They are highly likely to survive the early ages of childhood and adolescence, but typically die off in their older age. Great examples of type 1 organisms are whales, tortoises, humans, and other animals such as dogs or gorillas. Type 2 is called the constant loss curve, and this may be pretty intuitive. An organism that is a type 2 survivorship has an equal chance of dying at any point in its natural lifespan. These include squirrels, some other rodents, and particularly songbirds. Lastly, you have a type 3 curve. This is called the early loss curve because the majority of organisms in this species tend to die off in the early years of their lifespan. However, if they survive those early years, they are typically pretty likely to survive to the end of their lifespan. Great examples of type 3 curves include most plants and bacteria. Okay, so up to this point, we've talked about the way population growth should look. Now let's talk about human beings who never really do anything the way that we're supposed to. This graph shows you human population as far back as we can think about it. We're starting more than 2 million years ago with the early rise of Homo sapiens and other hominids. As you watch this population change, you will notice one of the first places that's important is the advent of agriculture. This is called the Neolithic Revolution, and that happened about 8,000 before current era, or BCE. As you watch the population move closer and closer to today's year, you will see that that population number tends to remain pretty steady, although it does grow slightly from about 5,000 BCE up to about 0 AD. When we get into what's termed the Middle Ages, around 1000, you start to see population growing until you reach this very specific dip. This dip was the Black Plague in Europe, which killed approximately a third of the known population. By 1600, we're starting to expand across the globe in our race to discover the New World, or rediscover the New World from people who already lived there, and our population starts to grow. Once we hit the 17 and 1800s, the Industrial Revolution is beginning, and population booms as people move from agricultural to urban areas. The more people you have working in a family, the more income you have. Population booms exponentially. By 1950, we've hit about 1 million people. Not long after that, we hit 2, and then 4. And in 2020, we are at almost 8 billion people. There were 3 points over the human population span that caused global population booms. We've already mentioned 2 of those, the Neolithic Revolution and the Industrial Revolution. But one of the first ones that really allowed our population to rise above the level of near extinction was the discovery of fire and tools. Once we did that, we made everything else possible. Please do not think that the baby boom in the US and some other European countries led to a global worldwide population boom. That's not necessarily how it happened. If you look at this graph, you'll notice that the human population looks nothing like it should. We are technically considered K-selected species, which means we should, in theory, have a carrying capacity. While some have postulated that the human carrying capacity is 10 billion, some have mentioned that it's lower. We honestly don't know what the human population carrying capacity is because we've used technology so much that we have pushed the boundaries of where and how long we can survive. This is called the human paradox. We should, by all rights, be a K-selected species, but our growth definitely resembles our selected species. So here's the problem with the human paradox. It's this thing called Malthusian population growth. This comes from a guy named Thomas Malthus, who was an Irish philosopher who started talking about population growth. And specifically, he was talking about controlling the population of the Irish. Malthus postulates that population growth is exponential, while resource growth is linear. This means at some point, population growth will exceed the resource growth. He called this the point of crisis. You'll see this in the graph at the lower left-hand corner of your screen. You also see it reproduced in A on the right-hand side of your screen. You'll notice that there's a difference between inadequate food and food surplus. Normal Malthusian population would say that we have outstripped our resources by a wide margin, and we should in all rights be dying out. But that's not exactly what's happening with us. Of course, there are things happening in the world today, such as the spread of COVID-19 and other infectious diseases that do have a high mortality rate in certain populations. We're not actually dying off at the rate that you would expect. That is because we have innovation, we have technology, and that technology has pushed the boundaries of that point of crisis so that we aren't experiencing the drastic effects of loss of resources that we typically would. When we talk about agriculture, one of those innovations we talk about is going to be the Green Revolution, which is the development of genetically modified and genetically engineered species. The point here is this: human populations should not be as big as we are. Malthus has predicted it. We should let the lack of resources do what it naturally does and cull the population. But human beings have used technology to push the boundaries of our carrying capacity and to innovate in ways that, in theory, should provide every individual on this planet with enough resources to survive. So to this point, we've talked about how you can intuitively identify what the rate of a population growth might be by looking at its designation, its reproductive rate, its survivorship, and its interactions with other species. We've talked about the human paradox, and we've talked about how we are the exact opposite of everything Malthus says we should be. Let's talk about how we mathematically understand population growth and the impacts that has. There are a total of 6 important population growth equations that you should have memorized and understand. I can guarantee you're going to be asked to use these on my tests and on the AP exam. The first one is total population change. This is what we're looking for, the actual number of people, or in this case humans, so we're talking about people, that a population has grown or decreased by. Total population change can be a negative number. The best way to figure out total population change is to add your births and your immigrations, and then subtract the sum of your deaths and your emigrations, or your individuals leaving your population. So total population change equals birth plus immigration, those coming in, minus death plus emigration, those leaving. This can be a negative number, which indicates your population has actually decreased. The second is annual growth rate, also known as rate of natural increase, RNI. In order to calculate this, you need the crude birth rate and the crude death rate. Crude birth rate and crude death rate are both represented as a number per 1,000 individuals. To find your annual growth rate, it's crude birth rate minus crude death rate divided by 10. This will give you a percentage. For the most part, annual growth rate will be positive. However, there are some populations, such as Japan and Germany, that are getting to the point where they have more elderly people than they do younger people. Therefore, their death rate is actually going to be higher than their birth rate. Next is doubling time. Doubling time is also known as the rule of 70. It's found on average with a population annual growth rate of 1%. It takes approximately 70 years for the population size to double. So in order to figure out our doubling time, we take 70 and divide it by our annual growth rate. Do not change your annual growth rate into a decimal. If your annual growth rate is 1%, you divide 70 by 1, not by 0.01. Never convert your annual growth rate to a decimal. Your doubling time should not be negative. If your doubling time is negative, that indicates that your population is going to be dropping, and you're not typically going to have an answer for that. It's almost impossible to see a negative doubling time on the AP exam. I've never seen one. You have total fertility rate. Total fertility rate is the number of births per woman over her lifespan, and it begins at the time she becomes reproductively active and has her first child, and goes until the point where she is no longer biologically able to have children. This is an average of all births over all women in a single population. So to figure out total fertility rate, it's number of births divided by number of women. This is typically given in just a number. Total fertility rate is 2.7, for example. Then you have population density. This is important when you're trying to understand things like disease transmission or poverty. Population density is really simple. What's your total population? Divide that by your total land area. This is given in people per kilometer squared. Finally, your urban to rural ratio. This tells you what is the difference between your urban and your rural population. To do this one, the best way to do it is, what is your urban population? What is your rural population? Simplify those numbers down to the very simplest ratio. For example, 3 to 1 or 2.5 to 1. These are important population formulas that you should be familiar with. The first 4 are the most common ones that you will see and require calculation. One of the biggest things that's going to impact the rate of your population growth as a human population is your infant mortality rate. Typically, this is identified as the number of babies that die before they reach their second birthday. Areas with very high total fertility rates, or TFRs, tend to be associated with areas of very high infant mortality. This is because the goal of reproduction is to get your genes into the next generation. And if it's highly likely that the majority of your offspring are going to die in infancy, you tend to reproduce more in the hopes that you will have at least one child that reaches adulthood. The graph on the lower left shows you the rate of infant mortality across the globe. You'll notice that those areas that are in red are those that have a very high infant mortality rate. They are strongly associated in Saharan Africa, largely because these are areas that have high total fertility rates, but are also subject to a lot of different diseases, particularly malaria and other diseases that can affect immunocompromised children very quickly. If you notice, the US isn't so great, but it's not horrible. Our infant mortality rate is 5.8, meaning for every 1,000 births, approximately 6 children are going to die. The global rate, however, is 32, which takes into account those outliers of those very, very high populations in Africa and part of the Middle East. Total fertility rate is strongly associated with that. It's also strongly associated with income. If you look at the graph on the right side of your screen, you'll see that the total fertility rate globally is pretty good. Niger has the highest total fertility rate in the world. It's approaching 8 babies per woman. Niger is also one of those countries that is bright red in the infant mortality population. So if you notice, those places that have a very high total fertility rate are also associated with having a very low income. Again, the more children you have that can survive, the more workers you have, the more money or food you can bring home to the entire family. So Niger, Somalia, Angola, the Ivory Coast, Liberia, those are places that have a very high total fertility rate, but also a ridiculously low per capita income. Then you start getting to what we think of as the developed countries. You'll see China has a very low total fertility rate. It's actually below 2. Russia is the same. Japan and Germany, the US, they all have a total fertility rate lower than 2 births per woman, and that's a problem. There's this thing called replacement fertility rate, or RFR. Replacement fertility rate is how many do you need to keep your population stable, and that number just happens to be 2.1. Why the 0.1? It helps to take care of that infant mortality rate, and also people who choose not to reproduce. It takes 2.1 births per woman to ensure that the population remains stable, because those 2 children replace the parents. China, Russia, Japan, Germany, the United States, Luxembourg, they all have a total fertility rate lower than 2.1. So what does this mean about their population? When we start looking at demographic transition and we start looking at age-sex diagrams, those are going to be the countries that start to have this bottom contracted graph, and their population is actually declining. So we've talked a lot about human population. There are basically 2 types of graphs that can show you everything you really need to know about a population and its growth. One of these is an age-sex diagram, or a population pyramid. These population pyramids show you the proportions of the population that are made up by individual age groups, as well as cohorts. These cohorts make up 3 different groups. The pre-reproductive, which are typically 0 to 14 years old. The reproductive, which is typically 14 up through 44, and the post-reproductive, which is 45 and above. You will hear me use these terms, and in these graphs, they are indicated as pre-reproductive in dark green, reproductive in light green, and post-reproductive in kind of a yellowy looking color. We're going to start with A and work our way around. Note that these are not necessarily in the order that you may see in your textbook or your review book. So let's start with A. A is showing what we typically know of as a rapid population growth. The base is very wide compared to the point, and the pre-reproductive cohort is the most abundant one. You see this kind of population in areas in Africa and in Latin America. Let's look at B. B is showing us that while our population may be slightly dropping, it's actually going to be pretty constant if you look at the differences between each of the different cohorts. The numbers are relatively the same. This is what we call stable population growth. The U.S. is currently in this kind of population growth, but it is beginning to transition to what we see in C. If you look at C, the pre-reproductive cohort is ridiculously small compared to the post-reproductive cohort. This is what we call a declining population or a negative growth population. This is because our deaths are going to far outstrip our births, meaning our population growth is going to drop. Germany and Japan are fantastic examples of this kind of population pyramid. Lastly, in D, you have what is called slow growth. It may not look like that on the surface, but that's really what it is. You'll notice that your pre-reproductive cohort is getting bigger, but it's not very big. Your reproductive and your post-reproductive cohorts are larger in comparison, but your pre-reproductive cohort is starting to grow a little bit. This is what we call slow growth, okay? We are going to lose some people in our post-reproductive cohort. Our pre-reproductive cohort is going to be getting slightly larger, and our reproductive cohort is large enough that they can have more children. So this population is going to be growing, but very slowly. This is indicative of China post-one-child policy. This is the second graph that can tell you pretty much everything you need to know about a population and its growth. This is called the demographic transition model, and it looks at the rate at which a population moves from being pre-industrial, mostly agrarian, through to a post-industrial society. Demographic transition looks at three basic things: birth rate, death rate, and population size. And it indicates various different factors that allow for this to happen. So let's look at each of the four major phases, and then we'll start talking about the proposed fifth addition. So phase one is the pre-industrial population. The population size is very low because your birth rate and your death rate are very high, but also very similar. So you're not really adding any new members of your population. Phase two is transitioning. In some cases, it's called industrializing, but we will call it transitioning. This is a period of rapid population growth. Typically, it's the introduction of increased sanitation and perhaps some better medical care. Your birth rate drops a little bit, but not exponentially. But your death rate drops dramatically. And when birth is higher than death, you get a rate of natural increase, and your population starts to grow. And it starts to grow rapidly. By phase three, industrialization has set in. It's less beneficial to have more than one child or large families. So births start to drop because people get an education and they tend to have fewer offspring. This causes your birth and your death rate to become closer together again. Although you still have an increase in population, it's not as dramatic as it was in phase two. In phase three, that population is continuing to grow, but it's starting to stabilize. Phase four is the post-industrial. At this point, your birth rate and your death rate are almost the same, and your population levels off. Post-industrial societies are those that are indicated by large amounts of healthcare, large amounts of higher education, and lots of technology. Demographers have now proposed that there is a fifth stage of the demographic transition model. Stage 5 is called declining. And that is because we are seeing in some populations, like those in Germany and Japan, that the death rate is starting to get higher than the birth rate. And when your death rate is higher than your birth rate, you have a negative rate of natural increase, which means your population is going to start getting smaller. We don't quite know what happens after that. But for our purposes, there are 5 stages of the demographic transition model: pre-industrial, transitioning, industrial, post-industrial, and declining. So this is the big thing about population. This shows you your population pyramid and your demographic transition model overlaid together. A population that goes through each of the 5 stages of a demographic transition model is going to have a population pyramid that looks very similar to the ones that are indicated for each level. If we looked at the history of Japan, we would see that in the early ages of life there, it was a very rapid growth. As they moved through the transition to industrialization, they started getting a little bit more stable population and eventually it started to slow down its growth, and now they have a larger elderly population than they do new individuals. So they have what's called a contracted pyramid. The base is much narrower than the rest of it. You've seen this equation before. This is the iPad equation. Let's review this really quickly as we start to talk about the impacts of population growth. So the total impact of an individual or of a population is equal to the population size times affluence, which is measured as consumption per person, times technology, which is measured as the impact per unit of consumption. Larger populations are going to have larger total impacts. That's something to think about. A lot of impacts of population growth, and some of them probably seem pretty intuitive. Areas with high population, especially high population density and low total income, can have large amounts of diseases due to poor sanitation or lack of accurate and correct medical care. These diseases can transmit very quickly. Also, they can just transmit because of large numbers of individuals. Examples of these include cholera, influenza, HIV, which is through person-to-person contact, and dysentery. You can have nutritional deficits due to lack of access to quality food, which can lead to malnourishment, undernourishment, or even overnourishment, and specific diseases such as kwashiorkor and marasmus. And it can also lead to conflict over scarce resources. The impacts of population growth on the individual is really going to look at, are they in a developed or developing country? Developing countries tend to have larger problems with disease, nutritional deficits, and conflict. This isn't to say, however, that developed countries are immune to these problems. So let's talk about it. We are living the AP environmental experience today. We have the COVID-19 global pandemic. COVID-19 is a disease that currently we don't have a real treatment for because it is a novel virus. We haven't seen it before. But let's first talk about how diseases are transmitted before we can kind of start talking about how COVID-19 fits into this idea of population and disease and why we're all sitting at home right now rather than being out at school. There's this thing called herd immunity. And herd immunity protects those individuals who either can't be inoculated or vaccinated against the disease, or those who choose not to, although they are a problem on their own. Herd immunity protects individuals who are not immunized, who are sick, or who are contagious or immunocompromised. The larger number of individuals there are in a population who are immunized and healthy, the fewer number you're going to have of those people who are sick or contagious. This is because it makes it harder for the disease to move from one person to another if large numbers of the population are immune to it or are immunized against it. We talk about herd immunity because we also have this transmission factor. This is how many people one sick person can transmit the disease to. And you'll see this graph on the right-hand side of your screen. One diseased person can exponentially impact a population. If you look here, one diseased person on average infects 2 people. Those 2 people infect 2 people. Now we're at 4. Those 4 impact 2 people. Now we're at 16. And it grows exponentially until one infected person has dramatically changed the health and safety of an entire population. This is one of the reasons why social distancing is a good way to slow the rate of a population disease. The point of social distancing isn't to stop a virus. It's to slow the rate of spread so that hospitals and medical care is not overwhelmed in having to treat this disease that we haven't really seen before. Let's look at how COVID-19 compares with other infectious diseases. And we're looking at this by mortality rate and basic reproduction number, or how many individuals does one sick person infect. You'll notice that COVID-19 is down near the bottom, actually. It has a basic reproduction number of about 2.5 and a mortality rate of about 2 to 3%. Now, these are pretty new numbers. We have new testing kits who are going out and new cases that are being identified globally. The thing to remember is that COVID-19 for an individual who is otherwise healthy isn't really a huge health risk, meaning that they're probably going to have some flu-like symptoms, feel cruddy for a week or two, and then feel better. Those populations that are immunocompromised, such as the elderly or the very young, or those who have diseases like cancer or other autoimmune diseases, those are the ones who are more likely to be at risk for a mortality from COVID-19. If you look at some of the other diseases that are indicated on here, you'll see the influenza, which is your typical seasonal flu. That has a lower basic reproduction number and globally a lower mortality rate, largely because we have pretty good ways of treating it now if people have access to health care. You'll see H1N1 has a very low basic reproduction number, but a ridiculously high mortality rate. Same thing you'll see for tuberculosis. Tuberculosis, smallpox, polio, diphtheria, mumps, pertussis, and measles. These are all diseases that we have at this point vaccines for. And at one point, these diseases were almost completely wiped out in the developed world. And they were completely wiped out because of vaccinations. Look at these diseases. While mumps, pertussis, and measles don't have a very high mortality rate, they have a ridiculously high basic reproduction number. They infect a lot of people very quickly. This is why vaccination is ridiculously important, and it's a big part of herd immunity. The more people who are healthy and immunized against a disease, the slower at which that disease is going to spread, and the fewer vulnerable populations it can impact. Keep this in mind. So, we've talked about herd immunity. We've talked about basic reproduction number and mortality rates of diseases. Let's clear up a couple of those terms that you're hearing when it comes to COVID-19 or the coronavirus. One thing that you need to know is that the term coronavirus is a description of the physical virus itself. What does it actually look like? And we actually have several known coronaviruses that we've dealt with before, such as SARS and MERS. So keep that in mind as we start talking about the different kinds of diseases and how we might treat them. We typically categorize diseases based on 3 characteristics: the type, the location, and the methods. Let's talk about type of disease first. A disease can be considered either chronic or acute, and this is generally talked about in terms of how fast does it come on and how long and severe are the symptoms. Chronic tends to be slow acting and long lasting, but with less severe symptoms than acute. We can also look at a disease in terms of being seasonal or novel. A seasonal disease is one that typically occurs in the same conditions around the same time every year, although there may be variations in the genetic strain, such as the flu. A novel virus, such as COVID-19, is a disease that we previously have not seen in human populations before, although we may have seen it in other organisms. In this case, COVID-19 is thought to be a zoonotic disease, meaning it originated in an animal population and was transferred to human populations. We can also talk about disease by its location. An endemic disease is one that is in numbers that are normal for the country. You expect to see around this many cases of the disease in any given year. An epidemic is a higher than normal number of a disease in a given country. While it may not be a great increase in number, it's still higher than you expect. A pandemic, such as what we have with COVID-19, is higher than normal numbers of a disease on 2 or more continents. So when you think about global pandemic, don't stress. All this means is that a disease has traveled from one continent to another. That's all. Then we can talk about transition methods or transmission methods. We typically talk about these in terms of being direct, indirect, fomite, vector, or reservoirs. Direct transmissions include person to person, being in physical contact with the individual, or through droplets, such as coughing or sneezing and releasing droplets into the air. You have indirect, which is waterborne or airborne. Waterborne includes fecal to oral contamination, which is when an individual comes in contact with water that is contaminated by fecal matter. This is one of the big things that transmits dysentery and diphtheria and cholera. Fomites are inanimate objects that can transmit a disease, such as door handles or tables. Various germs and viruses and bacteria can survive on inanimate objects for some period of time. That's why it's important to disinfect commonly used areas as often as possible. You also have vectors, which are living things that transmit diseases from one location to another. An individual can be a vector, but we also talk about them in terms of ticks, mosquitoes, other bugs, or other animals. And then you also have reservoirs, which are objects, areas, animals, or populations where disease is normally found. This is why you specifically identify immunocompromised individuals and limit their movement, which can prohibit them from going into contact with reservoirs. So let's talk about nutritional quality. One of the things that we talked about as an impact of human population is a lack of access to quality food. This can cause diseases that are related to being malnourished, not having enough nutrients or calories, undernourished, not having enough nutrients, or overnourished, having too many nutrients and too many calories. There are 2 specific diseases that we want to look at that are great illustrators of the problems associated with overpopulation and poverty. These are kwashiorkor and marasmus. Kwashiorkor develops in children whose diets are deficient in protein. And if you think back to all of those Sarah McLachlan videos of individuals in developed countries where they're asking for your money to sponsor a child, most often they're showing you children that have this kind of swollen belly. These are children that are suffering from kwashiorkor. In marasmus, it's due to a deficiency of proteins and calories. Individuals who are suffering from marasmus are ridiculously thin. You can see all of their bones. And they will eat until they can't eat anymore. But it's very hard for them to put on weight. So these are diseases that are associated with nutritional quality. They don't have enough protein, or they don't have enough calories. So let's talk about the difference between being undernourished and malnourished. An undernourished individual gets 90% of the daily calories that they need. But the difference is that they don't have access necessarily to quality food, quality fresh fruits and vegetables, proteins that they need to be successful in growing and maintaining their body's functions. Normally, individuals who are undernourished are associated with economic reasons. It's hard to get access to those good fresh fruits and vegetables. A malnourished individual has a shortage of nutrients. They don't get anywhere close to what they need. And this causes diseases such as marasmus and kwashiorkor, bloating abdomen, skin problems, lowered immunity, complete lack of muscle development because there's not enough nutrients to get that far. Your body's working overtime with the nutrients it has just to keep your heart beating and your lungs breathing. It's important to note that you can be overweight and be undernourished or malnourished. The difference isn't necessarily about the kind of amount of calories that you get. It's the quality of those calories. People who are overnourished, getting more calories than they need, and in some cases more nutrients than they need, can show symptoms of being undernourished or malnourished when they have difficulty remaining their health. So, the takeaway here, it's possible to be overweight and be malnourished. The lack of nutritional quality. Something we need to talk about is food insecurity. Food insecurity comes most often from poverty. An individual who is food insecure does not necessarily know where their next meal is coming from. And unfortunately, Guilford County is one of the top 5 most food insecure places in the country. Individuals who are food insecure often live in what is called a food desert, where it is a vast amount of difference between being able to get quality food and just being able to get food. Individuals who live in food deserts have to travel more than a mile in order to have access to quality nutrients, such as fresh fruits and vegetables. Food deserts often have a high instance of fast food restaurants and areas that produce quick calories, but not necessarily quality calories. Individuals who are food insecure tend to either follow the overnutrition policy, where they tend to be obese because they are eating calories that aren't necessarily good for them, and have what's called hidden hunger. You don't necessarily see it. Or they're undernutrient, and they have the hidden hunger and nutrient deficiencies. The United Nations has developed the Global Sustainability Goals. These goals are designed to address all of the problems of overpopulation to help make the world a better place. And the first 2 of those goals deal with poverty and hunger. How do we, as a society, eliminate poverty? How do we ensure that every single person on this planet has access to quality, sufficient nutrients? The truth is, there's enough food on this planet to feed everybody. We don't have a food problem. We have a distribution problem. Here are a couple of the other global sustainability goals from the UN. We've looked at reducing poverty and hunger, but let's look at some of these others. Health and well-being, education, gender equality, clean water and sanitation, and reduced inequality. One of the things that you should see here are access to quality healthcare, education, and reduced inequalities among populations and among the sexes and genders is a key to changing our population. And we've talked about this before. The key to solving overpopulation is targeting conditions that women live under. If women have access to quality healthcare, including family planning, contraception, and yes, even abortion practices, they're more likely to be very mindful and deliberate about the way that they reproduce or choose not to reproduce at all. Women who have access to quality education, especially higher education, tend to get married later, have children later, and have fewer children. And when women have the choice on whether they want to get married or go into the workforce, or whether they want to have 1 child or 5 children, that choice and all of the information that comes with it helps us to maintain and drastically slow the rate of our population growth. So if you want to solve the overpopulation crisis globally, Do exactly what Bangladesh is doing. Target women. Empower them with education, with the ability to join the workforce, and with access to quality healthcare and family planning. That's the only way we're going to fix this problem.